talking today is essentially the continuation of our work on superconductivity, essentially on a disordered landscape. But instead of giving you the older result that I have been talking so far in many conferences, I will show you some new things, namely how does a disordered superconductor evolve with magnetic field. So this work was done in collaboration with these students and postdocs. These are the scientific staff, and Orumugam Thamijavel is my colleague who does mostly the sample growth for us. And Amit Ghoshal and Anurag Banerjee, in this work we collaborated with them on the theory. All right, so first let me introduce our toy. So I run a low temperature lab where we do scanning tunneling microscopy, broadband microwave spectroscopy, penetration depth, and many similar measurements. And what I would like to emphasize is that all our toys are not commercial, they are all home built. So this is one of our prize toys. This is the millikelvin scanning tunneling microscope, where you have, this goes down to about 350 millikelvin, and this has a magnetic field of 9 Tesla. So it looks like this. The real STM is sitting down below in the cryostat, where it can go down to 350 millikelvin. All that you see outside is essentially for vibration isolation, the cryogenic liquid container, and what you see on the top here is actually sample preparation. Because STM you cannot do on any sample if once you expose it to air. All that you get after exposing to air is garbage, because tunneling is from the surface and the surface is contaminated. So therefore, we have this chamber in which we prepare our sample if it's a thin film, or we cleave a sample and open a fresh surface if it's a single crystal, and then subsequently with the help of these manipulators, without ever breaking vacuum, we push it down to low temperature here. This is our STM head, and if you want more details, you should see this paper where we have published this design. All right, now of course, we also do pulse laser deposition, and pulse laser deposition cannot be integrated with the STM machine because it has a huge laser and so on. And therefore, when we do PLD, that's a different chamber, but again we never expose the sample to air. So we have this toy here, which is called a vacuum suitcase. So we prepare the sample and take it inside the vacuum suitcase, where we can seal it at 10 to the power minus 10 torr. It has a battery operated ion pump. You detach the vacuum suitcase, take it to the STM, put it in and do the measurement. So again the sample never sees air when we are doing STM on it. So it's up to here. Up to this gate valve, this entire thing is the suitcase. It weighs about 9 kg. So you can, this is now attached to the PLD chamber, the pulse laser deposition chamber. You can disengage from here, carry it anywhere, and then again engage this flange to the matching port in any other chamber where you want to transfer. UHV. And you can, people even use this to transport it across labs. So, yeah. We use, no. So for engaging here, we use neoprene gasket, not neoprene Viton gasket. You can cheat a little bit and yet get minus 10. All right. So to give you some example first of, this is for example a niobium diselenide surface. Niobium diselenide is a type 2 superconductor, and with the scanning tunneling microscope we can get these vortices when we apply magnetic field. So you can see this beautiful image of vortices. So this is a conventional superconductor, and I am showing you this essentially to show you how a conventional superconductor, the mixed state of a conventional superconductor behaves. So this is what we know. We have these flux tubes which have entered in the form of vortices. Now you can do spectroscopy along this line, and what you see, if you start from here, you have a well-formed superconducting gap. Then you go towards the center of the vortex. You know that the center of the vortex is a normal metal, and there you don't see the gap anymore, and what you see is this small peak, and then again you cross and go on the other side, you see the gap. Now the reason you see this peak, this essentially is because you are confining the electron within the size of the vortex. So this is called an Andreev bound state or a Karalimaki-Dogen ground state. And this essentially shows you that the normal electrons are confined within the vortex core. Outside this vortex core, you have Cooper pair, so there is Andreev reflection at the boundary. Okay, if you go to slightly more disordered sample, then this peak actually gets smeared out, but again you get something where the core of the the core of the vortex is a normal metal. So you have here at the core, you have a flat spectra, and you get a gap when you are away from the vortex core. Now, if you look at a larger area, what you see is that these vortices will form this kind of hexagonal pattern. And then as you increase magnetic field, the density of this vortex, this is the Abrikosov flux line lattice. The vortex density will increase as you increase magnetic field. And eventually you will also have order disorder transformation of the vortex lattice. And when you go at a field where this normal core come very close to each other and start overlapping with each other, that is what is defined as the upper critical field. That's where you lose superconductivity. So this is another system, an amorphous molybdenum germanium thin film. And again you see the same thing. With increasing magnetic field, you have a larger and larger density of vortices. This is the lattice constant of this vortex lattice with magnetic field. You can see that the lattice constant keeps on shrinking, and at some point the lattice constant will become of the order of the vortex core size, and there everything becomes normal. That has been taken. All right, so this gives you an overview of the conventional understanding of superconductivity, of type 2 superconductivity, essentially, which was initially formulated by Abrikosov. So the reason I showed you this slide is essentially to show you that for conventional systems, our machine that I showed you in the beginning sees conventional physics. So this is a reality check. Now I will show you a system, I will talk about the main topic, where nothing is conventional essentially. So the system that I will be talking about now is niobium nitride, and this is a simple type 2 superconductor in its clean form. It has a sodium chloride crystal structure. It has a high TC of about 17 Kelvin and so on. But what you can do is that here you can controllably change the level of defects during growth, and these defects come as point defects of niobium vacancy. Now as you increase this niobium vacancy, you can see that the resistivity, normal state resistivity increases, the TC decreases, and at some critical level of disorder, you lose the superconductivity completely. Now we characterize our disorder by this quantity, which is the Fermi momentum Kf multiplied by the electronic mean free path L. This, if you want, is a measure of mean free path in terms of de Broglie, in units of de Broglie wavelength. And what you observe is that as your disorder becomes higher, that means KFL is lower, around KFL of 1, your TC becomes effectively 0. For us, 0 means less than 350 milli-K, and your conductivity, which is essentially the inverse of what you see here, inverse of this axis, the conductivity, normal state conductivity also falls off precipitously. Now, having observed this, now this limit is where we have a fairly ordered niobium nitride without any defects. And this limit is where you have very disordered niobium nitride and there are vacancies. So you have the vacancy density that keeps on increasing gradually as you go to larger and larger disorder. Now let me apply our toy, the STM, and I will first take a film which is here. This is not a very strongly disordered film, so it's somewhat moderately disordered. So the TC has come down to from 16 Kelvin to about 9 Kelvin. Hello, yeah. Okay, so here when I do, let's say, the tunneling spectroscopy along a line, what I see is that I have a superconducting, this in zero field, I have a superconducting gap everywhere. However, what I see is that the height of this coherence peak is position dependent. So if I plot the height of the coherence peak, I get this patchy kind of structure. And what I will be assuming is that this height of the coherence peak, is proportional to my superconducting order parameter. So superconducting order parameter, so height of the coherence peak above the normal state background, so above 1. And therefore, I have a finite superconducting order everywhere. However, the strength varies. So I have a landscape which is somewhat disordered. Now here, however, if I now take the average of all these spectra and I calculate the superconducting gap and I look at the superconducting gap as a function of temperature, what I see is that it follows perfectly the BCS expected variation. So the superconducting gap follows like this green line and it drops to 0 exactly at TC, and TC is defined as the point where my resistance appears in the resistance versus temperature measurement. However, now, and this is actually the central paradigm of Bardeen-Cooper-Schrieffer theory. Okay, now let me take a sample which is strongly disordered. So here I have a sample which has a TC of 2.9 Kelvin. So we have of course data for many samples, but I am just choosing 2 for the lack of time. And what you see here, for such a sample, you get these 2 kinds of spectra depending on where you are doing it, and this is statistical. In some places, you see a coherence peak here, of course somewhat suppressed. At some places, you see the gap, but there is no coherence peak anywhere. You also see a slight inverse correlation. Where you see this coherence peak height, you have this zero bias density of states which is smaller, and where you don't have this coherence peak height, it's as if this spectral weight has come below the gap close to 0. Now I do this measurement not just at 2 points, but over a grid in a 200 nanometer by 200 nanometer area, and I plot this average height of the coherence peak at positive and negative bias. So H1 plus H2 by 2. And now you see that you form this patchy pattern where these blue regions are where the coherence peak is completely suppressed. So effectively, if you don't have the coherence peak in the spectra, it's an insulator, because you have the gap, you have no coherence peak. On the other hand, these light regions are the regions where I have a finite coherence peak and their strength of course varies. This is a disordered landscape. And instead of doing this, I could have also looked at the zero bias conductance, and then I will see an inverted image. Here whatever is blue, here it becomes red, and actually this inverse correlation you can see in the 2D histogram, which has a weak negative slope. Now let me take this sample, the same strong disordered sample, and track these domains that I now see, domains or puddles or whatever you want to call it, as a function of temperature. So 500 millikelvin, this is how it is, 1 Kelvin, nothing much changes, 1.7 Kelvin, still it's similar, 2.2 Kelvin, it's sort of the regions which are blue, these are here the superconducting regions. They keep on shrinking and this sort of non-superconducting region expands. But now I go to 3.6. 3.6 is above TC, and yet the regions that are these blue regions, which are these regions where I have superconducting correlations, have not disappeared completely, and they keep on persisting up to about 6.9 Kelvin, which is more than double of TC. So what I can do is, instead of looking at these maps, I average over all the spectra, and what I am plotting you here is this color coding is the conductance, this is the voltage axis, bias axis, and this is the temperature. So this blue region will essentially correspond to this low conductance, so that's the gap, and this red region, dark red region is the coherence peak, and at high bias what you have is somewhere close to 1. So now when you see this, look at this. Your gap gradually disappears and seems to disappear around 7 Kelvin. However, on the same sample, if I do resistance versus temperature measurement, my TC is at 2.9 Kelvin. So I have completely violated the basic paradigm of Bardeen-Cooper-Schrieffer theory, which is the superconducting gap should disappear where my resistance appears. I have now two energy scales. One energy scale, which is, or rather two temperature scale. One temperature scale is the TC, and the other temperature scale, I call it T star. This is what we refer in our paper as the pseudo gap temperature. And there is a very similar phenomena in high TC also, which I think has a very similar origin, which is the temperature where my gap actually disappears. Okay, so this is the state that we call the pseudo gap state. Essentially, you have a gap reminiscent of a superconductor, but no superconductivity. We also observe one more interesting thing is that when you go to strong disorder, the gap is no longer the energy scale that determines superconductivity. This is a sample with a TC of 1.6 Kelvin. This is a sample which has a TC which is double, more than double, 3.5 Kelvin. There is somewhere in between. But all of them, the superconducting gap is about 1 milli-electron volt. So what has happened is that this superconducting gap now has become an irrelevant energy scale, both from the standpoint of TC as well as from the standpoint of temperature dependence, because you see that the gap persists above superconducting transition. So what could be happening? So this is something we have explored in great details over several years, and what we believe is the following. When you start from low disorder, here you have just one energy or temperature scale, and that is TC. TC and T star are the same for a BCS superconductor. As you go to stronger disorder, TC gradually comes down, but you have these gap which persist. So therefore, you get two energy scales here, one which is TC and the other which is T star, and in between these two, you have this pseudo gap state. What we showed through many measurements, and I will show just one of them, is that what happens is here the system becomes extremely susceptible to phase fluctuations. So even if your Cooper pair remains as entity, they cannot remain in a phase coherent state. So here the pseudo gap state is where you have phase disordering, which has given you a region where Cooper pair exists, but you do not have long range phase coherence. I will give you just one proof of that. So what I mean is that gap is no longer the energy scale. So what you should ask is, what is now the relevant energy scale here? Because in BCS theory, you have just one energy scale, that's the superconducting gap. The second energy scale that you can think of is essentially the phase stiffness of the superfluid. Because just having pairs does not ensure superconductivity, these pairs also have to be in a phase coherent state. So if I take, let's say, one pair here and one pair here far away, and I try to twist their phase, what is the energy cost? This energy cost can be calculated from simple Josephson relations, and what you get is an expression of this form. you have some numerical prefactor here, and here you have the coherence length and the penetration depth. You put this number for a clean conventional superconductor, lead or niobium tin. What you get for J, this superfluid stiffness, is a humongous number, 10 to the power 5 Kelvin or 10 to the power 4 Kelvin. So therefore, it's an irrelevant energy scale. It's so high an energy scale, you will never excite phase fluctuations. But what happens when you go to strong disorder? To look at this, we had to build another toy, and that toy is for the measurement of the superconducting penetration depth. Now, I won't go into the details. This is the two-coil mutual inductance technique, which is extremely powerful because it gives you the absolute value of the penetration depth without any fitting parameter, without any proportionality constant. So, at every temperature, you can get the value of the penetration depth. What you do is that you do a mutual inductance measurement, and then you calculate the full electromagnetic response through finite element analysis. Okay. Through finite element analysis by solving the London and Maxwell equation together. When you do that, you see for films with different TC, this is how my penetration depth varies. Now I take the penetration depth and coherence length and convert it into this superfluid stiffness energy scale J, and what I see is that as I go to stronger disorder, lower TC, my superfluid stiffness gradually drops. I plot in the same scale the superconducting gap energy scale. Now look at what happens. This end is where I am at very low disorder. So here superfluid stiffness is an energy scale that's at least 1 order of magnitude larger than the gap. So it's a irrelevant energy scale. Everything will be essentially determined by the weight temperature variation of the gap. However, as I go to stronger and stronger disorder, my superconducting gap does not vary that much. This actually is known from the 60s from Anderson theorem. But what decreases is actually the superfluid stiffness, and at some point it becomes lower than the gap. So if I am at in this region here, this is where I will have phase disordering that will destroy my superconductivity, but the gap will continue to exist. So if you want a more physical picture, my basic entities as pairs will continue to exist, but they will not have long range phase coherence. And it is actually this range where you see the pseudo gap. In this range, we see nothing. So there, we don't see the pseudo gap, it's BCS. So this is entirely consistent. Okay, so this is the sort of scenario that I have this disordered landscape. So I have these superconducting puddles which are possibly similar to a Josephson junction network, but I have a large distribution of puddle size and a large distribution of coupling strength. So it's a disordered superconducting Josephson junction network. And therefore, what will happen is that at TC, I will sort of destroy my phase coherence, and as I go higher than TC, I will destroy it further. So I will have smaller and smaller puddles till I destroy superconductivity, till I destroy the gap completely. Okay. Now, in the last 2 minutes that GP would give me, let me just show you what I intended to show in the beginning, that's the mixed state. Now, let me take this superconductor, which is 9 Kelvin. This is what I started with. It looks like a BCS superconductor when I do this zero field measurement. And now I will apply magnetic field to see how on this moderately disordered landscape, magnetic field affects superconductivity. This is at 40 kilohertz state, 60 kilohertz state, 75 kilohertz state, the conductance map. What you see first of all is that these red points is where I have minima of this conductance, so that is where I see the vortices. However, here the vortices are extremely disordered, because these vortices are actually nucleating at region where my superconducting order parameter is lower. So it does not form any hexagonal lattice. It's an extremely disordered landscape. As I increase the magnetic field further, I get more and more vortices. Now if I look more closely, you can see that these vortices enter like these lines, like these chains, and they form this kind of a lamellar structure. So I start essentially segregating my regions, my superconductor, into regions where there are vortices, and since there are vortices there, it's the superconducting order parameter is suppressed, and they segregate my system into these whitish puddles where I have a robust superconducting order. So now, the other very interesting aspect of these vortices is the following. I told you in the beginning the vortex code has to be a normal metal within the Abrikosov flux line lattice picture. However, here when we do spectroscopy along these lines passing through the center of the vortex, what we see is this. Away from the vortex, we have a gap and the coherence peak. When I go to the vortex center, the coherence peak is nearly suppressed, but a soft gap still persists. Now, there is no way within conventional understanding of superconductivity that this can happen. We also observe that you have this zero bias conductance. If I look at it, then this is the zero bias conductance as a function of magnetic field. It gradually sort of, the distribution of this zero bias conductance start getting broader, essentially again telling you that as I apply magnetic field, I am getting into a much more disordered landscape. Now, to understand these results, we did a little bit of comparison with theory. This is a BDG simulation using a attractive Hubbard model, and here we increase the magnetic field through this Pearl's factor here. So, this kind of simulation Amit Ghoshal, Nandini and Mohit have been doing for many years. The additional thing here is to do this in magnetic field with this Pearl's factor. Now, this what I am showing you is for the clean case, again a reality check, that in the clean case I have exactly what I see in experiment. I have a vortex here. At the center of the vortex core, I have this huge zero bias conductance peak, essentially because of the confinement, the Andreev bound state, and away from the vortex core, away from the vortex core, I have this soft gap and this coherence peak. But if I go now to a disordered system, so I am going to a level of disorder within the model, which is very similar to experiment. I have a coherence peak here. And I have, if I make a map of this coherence peak, I have a mildly disordered landscape, just like what I have in zero field. And now, if I apply field, what I see is that I get this landscape becomes progressively more disordered, but the most important part is this. This is the calculated density of states from BDG inside the vortex core, and this is outside the vortex core. You see, within the BDG calculation again, I see a soft gap when I am inside the vortex core, which I do not see in the clean case. Now, of course, this is not a physical understanding because it is simulation. So, physically the understanding which I have is the following, is that a vortex core normally within a Abrikosov picture is a circulating supercurrent, where you have this current which goes as 1 by R. So, the current increases as you go towards the center, and at some point the kinetic energy of the Cooper pair is so much that it breaks the Cooper pair and you have the normal core. This is how you get the size of the core, which is of the order of the coherence length. This is the undergraduate problem. However, in the case when you have this when you have a strongly disordered landscape, it could be that locally your superfluid stiffness is a smaller energy scale than the gap. So, therefore, you do not have to increase the kinetic energy so much that the kinetic energy becomes equal to the gap. You just have to increase the kinetic energy enough that it is larger than the superfluid stiffness, and you get something that has no superconducting order inside, and therefore, there is no supercurrent anymore. But pairs will continue to exist because you have not exceeded the energy scale delta. Okay, now I think GP is getting very impatient, so I will stop here. I will just show this last thing. I showed you that if I start with something that is mildly disordered, apply magnetic field, it starts mimicking a very strongly disordered landscape. The final proof of that is that This is a sample with 9 kTc which doesn't have pseudo gap, but I keep on applying magnetic field. As my landscape becomes more and more puddle-like, the pseudo gap appears. And it keeps on progressively widening as I go higher and higher in magnetic field. This is my TC line. This is the T star line. In zero field, I have no pseudo gap. It looks like a conventional BCS superconductor. As I apply magnetic field, this appears. So the upshot of this is that this is not just applicable for this particular system. This is not a very strongly disordered superconductor either. Many of the superconductors that we study in the lab, polycrystalline samples, for example, could be very much in this disorder range. And if you are in this disorder range, in magnetic field, you can have things like upper critical field, quantities like upper critical field, that are no longer defined in the conventional Abrikosov sense. In the Abrikosov conventional sense, the upper critical field definition is only applicable in a clean system where you form a very well ordered lattice. So I think I will end here. Thank you for your patience.